if we have two cars, and this one desires to go this way, this one is going in the opposite direction. So we're trying to figure out, where does this car want to go? And based on the car going in the other direction, it should look at its own desired path, which is this blue arrow, compare it to the path of the other car, and then it might make some decision. Either maybe it'll go straight, it'll say, well, we're not getting too close, or it might kind of move away from the car, but still going more or less in the direction of the desired path. Now, if we have two cars that are going in the same direction, and one car is ahead of the other, now there's kind of a temporal aspect to this. So this car has an intended path that goes essentially inside where the other car is now, or where the other car was in the last frame, depending on the order of how we update the cars. This is essentially a line segment. It has a start point and an end point. This is also a line segment, has a start point and an end point, and these line segments also have kind of like a start time and an end time. This might represent frame n, and this might represent frame n plus 1, or it might represent some amount of time in the future. 100 milliseconds or 1 second, or the braking distance. And based on kind of the temporal alignment of these two lines, if we were to chart it out on a time versus space graph, let's use red. Make kind of like a Cartesian graph here. So we've got time, or no, maybe this is space. Well, space is usually the x-axis in physics diagrams, right? So this one is S, this one is t. Space-time. And this car at some time, it's in some location, but it's a little bit ahead of the other car. So it starts, let's say it starts here, and then after a certain period of time, it goes this way. This car, its desired path, let's say it starts kind of close to the origin, and it's going the same speed. So the algorithm's going to have to know that even though this one ends in the place where this one starts, it's going to have to, look at the difference in the time. Whereas the alternate situation, draw the same chart, just downwards, so that we don't have to draw over each other. still s, this is still time. So if we look at the case where the other car is coming the other way, and our desired path there's a collision here. And so the algorithm has to recognize that when they're heading in the same direction, that there's no collision because there's a difference in time. When they're heading in the opposite direction, there's a potential for a collision here. But of course, if this one wants to go really fast, there is a potential for a collision here. We also have to think about, what if the competing car is behind the other car? Let's see. Now, when the cars are heading in the opposite direction, we want them to head in the right, to head to the right. In the case of right-hand driving countries, so that essentially implements right-hand driving. So if we took this situation over here, but made it like this. So now our desired path, maybe it's heading kind of this way, and this one is taking a path kind of like this way. But really, if we're doing right-hand driving, then this one would kind of want to, cross over, but maybe we'll detect that there's a collision, and then this car will stop or slow down. So if there's a potential for a collision, it either has to move, it has to swerve, or it has to stop. And the same thing here, if this one, if they're heading in the same direction, but the car ahead is kind of just stopped, it's not making any progress, then, we have to, stop before the other car or move around it. So one strategy is we could think about, kind of different rays. Maybe we could do 3 of them or 5 of them. And the car chooses between the rays. Maybe it chooses like the longest ray that it wouldn't have to stop on, and that goes in the favorable direction. So it has a direction that it wants to go in. It casts some rays, in 5 different directions or so many different directions, and it each of those rays gets kind of clipped based on we're not. Yeah, okay. And then we can do the dot product with the desired direction. So if it's, moving away from the desired direction, then it has to, it's like it gets a lower score. So each of these rays kind of gets a score, which is basically the length of the ray, but projected in the direction of the desired direction. And each of these rays gets clipped by other competing cars as well as the walls. Yeah, I think that makes a lot of sense. Okay. Ooh. Ooh. Yeah, don't use a terminal as your... Don't use Vim. Let's see. So, I wrote this code here that does some crazy stuff. Oh, hold on. Okay, so that little gold circle is actually part of the next step, which is going to be test mode, the road building tool. So I'm working towards that in the background. But right now we're just looking at the cars avoiding other cars, or agents avoiding other agents. And I think before we finish, I'm gonna make some of these agents look like little people, so that we can get some idea of pedestrian simulation, which would just be the same algorithm, but with smaller objects. So this algorithm, which has a bunch of funky behavior, I was just kind of exploring some different things, and I'm just going to take this code and I'm going to strip out kind of the core part of the algorithm, but I'm going to keep the for loops, essentially. So let me just make a commit here. Funky vehicle behavior, and also test mode in it. Okay, so where am I going with this? So let's strip out everything I don't like about this old algorithm. I'm just going to calculate all of this stuff outside of the if statement, and between C++ compiler optimizations and the CPU's optimizations, I think that any unnecessary calculations won't actually occur. Let's see, we're not going to use a collision accumulator. Just going to delete everything I don't like about the old algorithm, because I have new ideas for the new algorithm. I kind of want to change P1 and P2 as well. I'm going to keep this if statement, but I'm not going to put anything in it. This agent has already been processed, meaning that as this for loop progresses, it's looking at so there's two different for loops processing the same list, and depending on the sort order of the two indexes, we might want to do a different thing because the timing is different. That one car is moved before the other. But right now I don't know what I want to be in that if statement, if anything. And I think as a first pass, I'm not going to look at the movement of the other agents other than to look at, are they heading in the same direction, because that's kind of important to know. And actually, I want to get a Boolean here so that we know. So Boolean is in same direction. Yes. Well, let's just have the last travel. Spec3, the last travel. And I think we end up reading that somewhere down here, but let's get to that when we come to it. I don't want to know what the tangent is, what the normal is. We're not thinking in that domain anymore. So we're just going to delete a lot of this code. I think I just want to delete all of this. And as a first pass, we're going to disable the smoothing that we were implementing before. Vec3 v travel equals n vector times travel. And then we could do v travel. Oh, not smoothed. Well, that's AI getting in the way for us, I think. That's AI getting in the way for us. And down at the bottom, I didn't capitalize it. Okay. I thought maybe I capitalized the T like that. Now, what did we say that we were going to do? So we're going to have like a const int, or I32, num raise equals 5. And then const vec3. Let's not initialize it, because we'll initialize it with a for loop. So we really want the raise kind of in the right direction. So cast raise from negative 45 to plus 45 degrees relative to the agent's direction. So to agent. Why am I still getting this wall hitbox radius? What am I doing here? Oh, okay. So AI's picked up the wall hitbox radius, 32 agent hitbox radius. We are also, I don't know if we'll keep track of the num collisions with this algorithm. In the previous algorithm, if it hit a wall, then it didn't look at the other agents, which created some weird behavior. How do we still not get? I'm trying to get the angle of travel. Thank you. Now, it's interesting programming with AI, because the AI kind of, when it gets, it's suggesting things that, like, you don't want, then that kind of tells you that you set up the code in a certain way, that you have certain variable names that you haven't bound, or that there should be a variable where you haven't gotten one yet. Let's see, angle of travel, angle step equals, can't we compute this? Some function of the number of rays. Well, this would be a 45 little spread equals m pi divided by 2, because this is really kind of 90. There we go. 32 start angle equals, yeah, sure. And then, well, hold on, no. Start angle was, don't we want to know the angle of travel? Yes, thank you. So it's okay. The algorithm that I programmed before that didn't get on video because the audio didn't record. I wasn't programming with AI, and maybe I'll turn off the AI or leave it off for a stream, and we'll see if I program differently, how I feel about it. I wouldn't say that I've become dependent on AI. Like, I'm still perfectly capable of programming without it. But it is nice. And it's hard to program now without ChatGPT when I get stuck or when I'm trying to figure out how to use a new API. So we actually want a collision. So let's say that we have vec3 point of collision equals let's say we call it POC equals point of collision. And then this is a function that we don't have yet. I think I have it in the New City Classic code base. Yeah. And we'll just go get it in a second, probably from the New City Classic code base. We don't want this to be the radar. Let's just call this the rays. And it's actually just a location in space. So it's pos, isn't it? Plus. And times travel. Right. Let me actually look, because how did the source how did the function in the old code base look like? So it was in utils. No, and we're just concerned about the API. Point line distance, nearest point on line. So, but this doesn't really give us any information about whether the lines actually intersect. But I guess that's the test that we're doing with the if statement. So it's if the wall hitbox radius. But let me just show this on the whiteboard. If we have two lines, but these lines actually have kind of an external shape to them. Hold on a second. Please excuse the crudity of this model, but basically each of these lines have a space around them, which is the hitbox radius, and so they might not actually intersect, but they'll pass the collision test. And then when we do nearest point on line, so let's actually call this nearest point on line. We don't really care about the distance. And well, hold on a second. because this function actually is only the nearest point to another point on some line. And what we really want is kind of the point at intersection. So do I have another function here? That really surprises me, that I never got a function that is basically just the intersection between two lines. I guess I just never got to that point. We have a line plane intersection, which, I mean, I guess in general, two points don't intersect in 3D space. But we're actually, this is really 2D space. We're dealing with vec3s, but the z is always 0, because we're not doing anything with the z-axis yet. Okay, so what we really want here is, if we have, this kind of situation where we have a bunch of different rays, and we have some line, we want to clip those rays based on the line. So I'm just going to quickly ask Claude 3, because Claude 3 has been pretty smart recently. Okay. So basically Claude is suggesting to get the intersection between the two lines, which we can do through some dot products and cross products. But then in order to say that the lines don't really intersect, it's suggesting to do this kind of vec3 infinity. Alright, so there's a function that I missed in the old code base, point of intersection, and I just want to look at this. This function might be computationally complicated, or require a lot of work. I don't know, for the computer, but for us, this isn't all that complicated of an algorithm. If the lines are parallel, projected closest point. Yes, this is basically exactly what we want. So segment A would be the ray, and segment B would be the other car. But here's the other thing: is we actually want to clamp the ray if it's within 3 meters. So maybe I'll try to explain that to Claude. Hold on, let me sort this out, because I actually think that I can reason through this. Maybe AI is not being so helpful tonight, or maybe I just don't know how to ask this correctly, but maybe it's a little bit easier to ask the whiteboard. Okay. So, we have some... Okay, let's get rid of this. We have some path that we're looking at. This is like one of some rays. So the car is casting some rays in some direction. And we have either a wall segment here, and it has a hitbox radius here. It has endpoints here, here. The green one has well, maybe the endpoint, is like here. And then obviously it's got its start point here. And if we just zoom in on the goal here, we've got some line segment that continues off in this direction. And we can get the point of intersection, and then we want to get the perpendicular, and then it's probably like the dot product to get this line. Is that the dot product? Or it's more like it's length, we like lengthen it by the dot product? Because what I actually want is this point here. This is the line that we actually get from the database, which is part of the road. These other two lines represent the hitbox radius, so it's like inflated out. It's like that kind of pill shape. This kind of like pill shape here, that's what we actually want to do collision detection on. The reason why I'm maybe overthinking this is because I actually want to get kind of like a deconstruction of this function Boy, it would be annoying to have to do this twice. I have to do it for the other agents and for the roads because of the way that I've organized these for loops. Well, okay, so maybe we can have a function that clips array. Okay, so clip ray, vec3 ray start, vec3 ray end. What am I writing? JavaScript here? I forgot how to write a function in C. Okay. And we actually want to have ready to like this is like the hitbox radius. And we actually okay, so when we normalize dot product let's see if Copilot figures this out. Okay. Well, this isn't really simplifying anything, but we actually want this to be ray end. See, we actually, this is why I want to deconstruct this function here. 22, what's going on? Okay, whatever. Yes, yank 22 down, thank you. Don't use Vim. Okay, so So do we have to get all the complexity of the distance? Why is this distance so complicated? Because it's actually kind of the same thing. Looks like this version gets both determinants. And it also actually handles the case where the lines are parallel. Whereas this one just nopes out. It's just like whatever. But I think that we do actually have to do something in the case that the lines are parallel. It's because, okay, so it's actually this t0 variable that is going to help us compute the thing that we actually want. But we want to add an extra little bit because there's a hitbox radius. Okay, and then this function is just computing, this is just for the intersection. But I don't think that we actually care about the intersection, or maybe we do, hold on. Okay, well, yeah, okay, so we want to get a t0 value, and then, well, it's a t hit equals 0, and then back 3 new end equals right end. And then in the parallel case, we're going to set t hit and new end to something, but I'm going to figure that out in a second. So this is t hit. And then we want to, depending on like, okay, so if this is coming in at like a shallow angle, it's got an intersection point here. And then we get this normal again, and we well, hold on, before we get to that. Maybe we can just, here, we can return PA, and in the case that they're parallel, we can just return new end, or ray end. And, yeah, sure. Now going down here, vector new right equals clip right. That's right, v1 wall hitbox radius, yes. It had some sort of suggestion of a, well, no, okay. And then for now, we're just not going to do the other agent stuff because I want to see if this algorithm that's right. We want it to default to kind of the middle ray. Well, I guess it could default to 0. Whatever. we just start at 1 here. Change this to best ray length. Okay. Vec3 v travel equals, yes. Okay. Now I just gotta get it to compile. So now the cars don't seem to be moving at all. All the rays get clipped down to length 0, it looks like. Okay. It looks like they all end up becoming clipped at some point. What causes this one to become clipped? Looks like all of them become clipped pretty much right away. But one holds on for a while. What on earth? And it looks like they're not really clipped inwards, they're just kind of, so we get a lot of T hit at 0. These numbers are not the same as before. Well, you know what's surprising? Oh, it's clamped to mag A. I see. Okay, so this starts out as this value. I was thinking that T was like a value between 0 and 1. But it looks like it's a value between 0 and the magnitude of A. Okay. Let's see what's going on. So if we have two rays that are not even close to each other, and this one's pointing this direction, then the closest point on the ray to the red line is here. But like, this red line is just way off in space. We don't want it to clip the ray at all, because it doesn't intersect with the ray. What it really means is if the ray is behind the vector, then we don't want it to clip. And what if the ray was kind of like here-ish? Because then, depending on like kind of where it's positioned, it might happen that the closest point is kind of somewhere along this line, but we don't actually want it to clip here either. Okay. So let's look at some of the original algorithms, because if we go down to where we have line intersection here, we actually get a PA and a PB, and then we do some clamping and some dot products, and there's how many different cases are there here? There's two, actually this is 3 cases, because there's an else if, so there's a possibility there's like an else case that is not being considered here. Which I guess just leaves PA the same. So there's 3 cases here, there's 3 cases here, so that's 9 cases. Then this if statement is 2 cases because there's a hidden else. And then there's 3 cases here, so 9 times 2 is 18. There's and then 18 times 3 is, I don't know off the top of my head, but maybe that's like greater than 60, I think. And then so there's actually like hundreds of different paths that these if statements could take. if you were to demarcate it all out. Well, I guess some of these cases are the same because these if conditionals are the same here. But there's a lot of cases. But okay, so dot. We actually want the dot A B, and then if the dot A B is, I think we want it to be less than or equal to 0. It looks like we're getting values, but I guess we don't. There's no printout if this dot product test doesn't pass. Okay, so I think we want to skip. We want to go back to, we were doing kind of like a line distance before. So let's get the dist here. And if dist is less than 20, then do some ray clipping. And 20 is just a bare constant. I'm just putting this value in there because it seems like a reasonable value. Okay, yeah, now we're getting some behavior. So, let's see. I think we want this angle spread to be more like a half circle rather than a quarter circle. Well, I've done something really wrong in my thinking here. Well, it definitely gets stuck. Why does it get stuck? We keep getting this t hit is 0. Okay. So this determinant over denom is essentially it's a parameter that represents how far along the line you are. And if it's negative, then you're before the beginning of the line. And if it's greater than 1, or if it's greater than mag A, rather, then you're past the end of the line. And so this clamp function clamps to the line between 0 and mag A. But I think we actually want to say Well, okay, so let's get uh, it's t along, let's call it, equals net a divided by denom. And then t along will be clamped here. But if the t along is less than 0, then there's no collision. So that's basically another version of the dot product test. Okay, this looks better. Look at that. A little janky, but okay. Why is it so janky like that? Let's see if it gets to the end. Ah, and maybe it got outside the wall. Doesn't seem to have a lot of respect for the wall. Doesn't even. Let's actually just make this rand, because we're not... And it looks like we don't use this t-hit here. Now it seems like it gets stuck almost. Okay, so we actually want to... This is what we want the dot product for here. I wonder if we have to normalize before we do our dot product in order for this to really make sense. Because the dot product has to do with like getting a kind of like a projected line that's the same as some other line. Let me just draw out what I'm... So this is what I was thinking about before, is we need to subtract from t hit this amount from the collision point to the hitbox radius. And somehow okay, so this is basically a right triangle here. We could also think about the right triangle here. And this value is the hitbox radius. This value is or this, yeah, how do I get this here? What is this? This length. Because then it's just Pythagorean theorem, right? But what is this length again? I guess it has to do with the angle. So this is why I'm thinking of the dot product. So let me just review what the dot product even is for a second. Well, this is weird. Why does it calculate cosine theta of... What is cosine theta doing here? Length of the cross spec. Okay, so we're actually already calculating, I think, the value that we need. I think it's denom. Okay. Hit. So t hit minus equals hitbox radius divided by denom. And then we clamp it again. This is a frustrating way to think about this problem. Let me go back to having multiple agents. Maybe we can see the behaviors a little better. Try to understand what's going on. I'll have kind of substantially the same behavior. Just see what the behavior is coming down. It seems to be a little better coming down. I don't know why. But they still get stuck here. And they get stuck way before the wall. That's really weird. There's something kind of surprising that, like, why is their behavior so chaotic? Let's go down here. I think instead of looking at the length of the rays, because it's a little random which ray is longest, I think we really want to we want a dot product of n vector. Is that right? Okay. Okay, so it's still getting trapped against the wall, but we're getting a little bit more sensible behavior. It knows to prefer the right direction. So I think that it's I think that what's happening here is if we've got some piece of road and we've got a car that's like gotten itself kind of trapped against the edge of the road here, and it's casting rays in all these directions. I think when it looks at this ray, it says, well, you're within the hitbox radius. So remember that this hitbox radius is like here. So it says you're within the hitbox radius already. So I'm clamping you to the end because the closest point on the end is here. But what it actually needs to say is, hey, this point is a lot better than this point. So I'd rather end up here than here because we're further away from the wall. So what is this? If the dot product of the normal is, so if we get a normal, um, um, yes, okay. And then if dot pubvec a I think it's actually greater than 0, or, well, hold on a second. The perpendicular might be, let's not think about it this way. Hold on a second. Really, we just want to know, is the end point further away than the start point? So we could get the sum of its distances from the two endpoints of the line and compare that to the sum of the distances. Yes. Okay. Okay. Well, that's like the opposite of the behavior we want. Okay, maybe I made my reasoning error here where I'm doing this dot product. Maybe that's not correct. What is the dot product again? Um, hey, I recognize this name. You know what? This concept, Banach-Tarski. Somehow you can construct two spheres out of one sphere, according to mathematicians. And I think the mathematicians are wrong about this. And I have an argument about why, which maybe I'll bring up at a later date. That's a rant for another time. Okay, so Okay. This is not what I want at all. I really do think that the dot product is what I want here, but I'm still not getting the behavior that I want, and I don't understand why. Shouldn't they all be the same length? Well, okay, so what if they just always go straight? Num raise over 2. Yes, okay. Oh, I see why. Because of the way that I did this for loop. So if I do something different here, well, I guess I could just do this and vector, and then I can keep this one here. I guess I'm prematurely optimizing. Okay. There we go. And now let's fix the wall collision detection stuff here. So let's keep that part. Still kind of getting stuck on the wall. And then down here, let's try the dot product method. See how that behaves. Okay. No. Let's try this method. Where if the ray is kind of further away from the wall, it's like they don't avoid the wall at all. Let's just make sure that the wall hitbox is big enough. I don't know. This has not been working at all. Okay, so we're gonna have some car. You tell I'm getting a little frustrated. This hasn't been going the way that I wanted to. I don't know why this is not... You know, last week everything was going so well. Alright. And it's shooting off a bunch of rays in some different directions. And what I've been trying to do is, if there's some collision which would be like a, what color am I getting? If I have a collision, which might be like some wall here, then I would crop these rays here, 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 which is the algorithm that I'm having so much trouble with. And then I would I would determine which one of these is the longest. And I'm also looking at, so these rays all started the same way, but we really like this ray a lot more than the other ones. So we want to give that one kind of like a bonus, and that's what I was doing with the dot product. But what I'm thinking is, instead of trying to shorten these rays, maybe I just want to like kind of count, like, for each of these rays, has anyone kind of like rejected the ray? And the walls should never reject the rays that are kind of going in the other direction. So the wall collision detection is just an if statement, because you'd always prefer to get further away from the wall. So it's really just a Boolean for every one of these rays. Has anyone rejected that particular array? And if it's been rejected, then the car has to stall. So I'm getting increasingly bogged down in this vehicle behavior algorithm, and I want to move on to something else. I think that this is something that I can come back to in a week or a month, and I might have some new ideas. I keep running into these same problems. They don't respect the walls. Yeah, very frustrating. So this is definitely something that we can come back to. So I made this tech tree for how I want to build the game. And as you can see, this part that I'm working on, agents avoid other agents, is kind of a leaf on the tree. It's doesn't really lead to anything else necessarily. And that's because of the kind of quantum simulation that I talked about before, that this part of the simulation is just for visual purposes. Ultimately, it's not going to feed back into the rest of the structure. It's just to kind of entertain the user, the player. So what I'm really going to start looking at is the road tool, because that ends up being kind of the core game loop of this game. And so what I'm thinking is that I want to start iterating on that. How are we going to build curved roads? How are we going to build different types of roads? And where this tech tree ends might surprise you. And I want you to focus on what's missing from this tech tree, because this is not the complete tech tree for the game. This is just what I plan to work on in the next, coming episodes. Some of this might be worked on behind the scenes. If it's just boring coding stuff. But where this tech tree ends is actually bus routes, which is the start of mass transit. And really, multimodal routing and bus routes, well, yeah, okay, so I'm going to do multimodal routing first, but multimodal routing is kind of the crown of this whole concept. And that's basically, okay, how does a person, get to the airport? Well, they walk out of their house, they walk, and then they find their car, which is parked somewhere, and they get in their car, and then they drive to like a park and ride, and then they get on the train, and then they take the train to the airport, and then maybe they get on another train inside the airport, and then they go to the terminal and get on the plane, and the plane travels. So there's a bunch of different steps over multiple modalities: walking, driving, taking trains, and so that's multimodal routing. And once I understand multimodal routing, then I'll figure out, are mass transit routes a layer on top of that? Are they, a substructure within that? How are we going to implement that? And, I'm trying to take my time and be methodical here. I'm not in a rush. Yeah. Lots of exciting stuff to work on. I reserve the right for this video series to take a day off and work on something else. So there's some other games that I might demo, just like web games, weekend projects. And I might also do a review of the New City Classic code, which is open source. You can find it on GitHub. Not a lot of people have engaged with that code, which is, I think, because it's not good code. And, maybe I'm not such a good coder at the end of the day. But, maybe with this video series I can try to improve and use more comments and explain what I'm trying to do better. So I can go over the New City Classic code, and, if people want to modify it, and, like if there's a part of the game that kind of just sucks. So I imagine that someone might try to remove a lot of the economic simulation and improve some of the flaws in the transportation simulation in the classic game, and I could definitely show how you might do that, and just make a city that grows perpetually and doesn't really have a real economic simulation, so you can just focus on the traffic, if that's what you want to do. And we are gonna have curved roads. We're gonna get to curved roads in the new game. So yeah, I hope you guys are excited.